Okay, we're doing applying the model, the third page, and here we're going to use CAPM and CVPM with our graphs to solve for anything that was unknown. So there are not a whole lot of things that are left unknown, so we'll go ahead and finish them all off. So for our first one, we want to work with the V graph. So we had a final velocity of 8.5 meters per second, and initial velocity of 0, and a delta t of 20 seconds over which our graph just increased. So there are two things that we don't know here. We know VI, we know VF, we know delta t, we don't know the acceleration, and we don't know the displacement during this interval. So the acceleration is the slope of the velocity graph, which would be this delta v, which is 8.5 meters per second minus 0, over that delta t. And that ends up being 0.425 meters per second, meters per second squared. Make sure you understand how those units work to get you that, which is, at the end of the day, kind of a pretty pokey acceleration. You went from 0 to about 20 miles an hour in 20 seconds, so pretty light. The displacement is also unknown. That's always the area under the V graph. So in that case, this displacement is 1/2 times this height, which is the VF. It's also the delta V. You could use either one here. Whatever relationship you find from your graph, that's fine to use. So that's 1/2 times 8.5 meters per second times 20 seconds. Check the units, make sure they come out to be meters as they should. And we'll end up we've gone 85 meters during this acceleration, so the better part of a football field. Okay, the second one is CVPM, so we're going to do our solving on a position graph. Here the x initial we can call whatever, 0 or whatever it is. The x final is unknown. What we really care about is delta x, how far it's gone. The delta t is 20 seconds. And the velocity, which is the slope here, is 8.5 meters per second. So we want to use the slope relationship here. So the slope of this is the velocity. It's 8.5 meters per second. Is the unknown delta x in 20 seconds. And I can solve, and the delta x will be 8.5 meters per second times 20 seconds. Check to make sure you understand how the units cancel. And that will give me 170 meters, which is twice as far as I got in the last one, because I'm going the 8.5 meters per second. I'm going that speed the whole time, rather than having to speed up to that and only get to it from the end. I could also have solved that one using the V graph. There's my 8.5 meters per second for 20 seconds. And so the area is 170 meters. Either way will work with that. We customarily do our problem solving with CVPM here, but this is okay too. Same principle. Alright, in the last one, we're starting at 8.5 meters per second. That's our VI. And we're ending at 0. And that happened over a delta t of 20 seconds. So our acceleration is again the slope of that graph, which is VF minus VI over the delta t. Because I ended at 0, I began there. And that will be negative 0.425 meters per second. Again, a pretty slow, so you must have seen the deer way off in the distance, because normally you would stop a little quicker than that. The displacement is, as always, the area under the V graph, so that's delta x is 1/2 times the height now is VI times delta t, which is the base of the triangle. So that's 1/2 times 8.5 meters per second times 20 seconds, which will give me 85 meters again. same as before. All right, that's it. That's everything we could possibly solve for in these situations, given this info, and it all came from the graphs.